it is important to understand that renewable oils have a very, very different chemistry from conventional fossil fuels. They are very rich in oxygenated compounds, which are not seen as much in fossil fuels. But also, there are some contaminants that we don't see either in fossil fuels, like phosphates, chlorides, in larger quantities than in any conventional fossil fuel. So, as you can envisage, you see that that feedstock is not suitable for conventional catalysts that use molybdenum sulfide, for instance. So the challenge is to, of course, do the reaction to enhance or change that feedstock into something that is useful, that can be produced as a fuel or an additive for fuels. What things happen in there is that those reactions, even though are known, because of the quantities of the oxygen in those compounds, you are producing a lot of water or CO2, which is not conventional in conventional fossil fuel treatment. So the catalyst suffers, conventional catalyst suffers with those environments as water and CO2 and the oxygenated itself will tend to deactivate the sulfide catalysts, which are the conventional ones. So some people are trying to figure it out how to use the same sulfide catalyst in fossil fuels. The only beautiful thing that renewables oil have is that they in general don't have sulfur. So conventional sulfide catalysts need sulfur in the feedstock to be keep activity. So because they don't have it, then the catalyst, conventional catalyst dies. So people are trying to contaminate or dope the bio oils with sulfur to be able to keep using those. So then the only beautiful thing that they have, you screw it by adding sulfur, and then you have to deal with H2S at the end and contamination of sulfur. So, as I mentioned, we need to get away from molybdenum sulfide or sulfide catalyst. However, the choices that most people know are noble metals. They are extremely expensive and not easy available because of the quantities. So if you try to do noble metals like palladium, rhodium, iridium, platinum, even gold for pharmaceuticals or fine chemistry, yes, that will work because those are the products are so expensive that then the catalyst is not expensive anymore. But for commodity products like the one we are dealing with, using those catalysts in large quantities is prohibited. I'm not mentioning is that the reactions that are being carried out in there produce a lot of water. You can have it depending on the condition. You can have liquid water and steam that usually those catalysts get poison for those environments. They deactivate, even though you can try to keep it. So you can imagine that they begin to oxidize even more, even further, and then you have to add more sulfur to the feedstock to compensate and to try to keep them alive. So that's the reason why here we went away from that and we begin to work on a different active phase that is the carbides. However, carbides have the advantage that they behave similar to noble metal, but as you can imagine, and there are several phases. However, carbides, molybdenum carbide, tungsten carbide has been known for more than 60 years. Even though, and there are several phases of they have been known to do similar reaction phases from you don't find a commercial catalyst for that. Even though the chemistry for more than 60 years they to produce them have been known to do stable reactions to you don't find a commercial catalyst for that because the chemistry to produce them stable configuration. There are many reactions that occur when the typical conditions of temperature ramping program to do the formation of the molybdenum carbide, for instance, the hexagonal phase. They tend to need to go to 700, 750 degrees C, usually in an environment of methane or ethane or some carbonaceous material that allows to do the formation of the carbide. Those conditions are tough. And because the reactions that produce one type of carbide or mixture of them or partially oxidized carbides are not very reproducible in large scales, I mean. So that makes that.
Well, you're one of the co-authors of the paper published on Science where we have proven that using carbides is possible. Years have passed since obviously you started that research, and we are now at a pre-commercial, but almost there. I would say capacity of our company to commercially distribute our processes with a canvas. But we have kind of crossed that bridge now. What can you say has been the difficulty and opportunity now that we are where we are with that catalyst?
The for that particular active phase, as I mentioned, there are several ways to produce that. However, those particular ways of producing that in small scale are feasible only at lab scale. When you want to go to a pilot or a commercial scale, you need to produce large quantities of them, 100 kilograms, a ton or more. So you need to be focused on procedures that allows to do that. So most papers you find tend to be around academic environments where the focus is to understand what the active phase can do or how to modify or do some things. But the main focus is not a scale up. It's not to produce even a supported catalyst because usually you work with the active phase as in the science paper you are commenting where we produce the active phase and we show that that active phase is able to do the reverse Waller achieved with 100% selectivity to CO, which is a very impressive result and granted us the opportunity to publish in the prestigious magazine Science. But when you go or when you want to go to pilot units that you require 100, 150 grams, or bigger units where you require 500 grams or 1 kilograms, the pure active phase, you have to distribute it on some support. And then it's when our knowledge or know-how enter into action because we know that active phase, so we were able to put it on top of different supports, and then we make something that is very equivalent to a commercial catalyst. We can support it in several different structures and shapes that allows to use different reactor configuration and different conditions. So we were able to do that in our pilot unit, and we were able to demonstrate in the particular case of bio-oils that is feasible. And we ran several bio-oils, and we were successful doing the hydrodeoxygenation of those feedstocks, producing something that in one of the examples we have 50% oxygen content, which have like 25% water as well, and we were able to convert that and leaving the hydrocarbon product with around 2% oxygen remaining. However, even though that 2% seems to be a little high for conventional fossil fuels, that particular feedstock is miscible with conventional fossil fuels, which is a very important advantage because right now many of those bio-oils tend to be used in doping or adding co-processing in FCC, for instance. But if you understand FCC, you know that adding those horrible compounds that are oxygenated are going to affect the catalyst later. So you or they found a way to get release of 1 to 3% of that co-processing in FCC, but they are affecting the catalyst of FCC. The other way is what we do, which is hydrodeoxygenation. But as I mentioned, conventional fossil fuels don't have that amount of oxygen. So the catalysts that are designed for treating them usually are not very good for that. So we were able to overcome that. We have a very robust catalyst that is commercially like or preparing with conventional unit operation of catalysts. We include preparation, mixing of solutions, impregnation, drying, and in this particular case, temperature treatments to allow to produce the catalyst. And that material can be handled with any conventional catalyst.
Me with something that would a short message to potential partners. And in our potential partners, I mean, it could be from the producers, because what I have found is that, we are coming from a different point of view from that value chain that exists today. And so we definitely are coming in with a more holistic point of view. We understand the feedstock well enough, not that we're going to provide them with ways on improving their feedstock, but we know the feedstock well enough that we can then now go to refineries and catalyst companies and be that liaison, that bridge. Because I think, just talking to Miles about how fragmented it's been in the past, where you have the producers producing an oil and thinking, oh, that's their problem to upgrade. And when they receive the feedstock, then they're being penalized because they can't unlock the full potential value of what they're
Exactly.
producing. So, what would you say to maybe any of our potential partners about our ability to disrupt a little bit in a good way the environment, the ecosystem that exists today with something like what we're doing?
The good thing about what we do is that we can sit between them and make a bridge, which is something that I see has not been done. People, as you mentioned, the one that produce the oil, they produce the oil, and then they are looking for who can use it. Green feedstock because of the penalties or the uh, greenhouse effect and policies, the political are struggling, as I mentioned. Then they begin to try to do crazy things that try to integrate or do co-processing in FCC is one of the most advanced ones, but they have to do 1 to 3%, maximum 5%, because it affects the outcome. So we are able to produce, to take those feedstocks, the original ones, make it something that is feasible for the refiners to use as, depending on the feedstock, as a additive. Because for instance, we have processed some bio-oil that produce very good diesel that is even so good that might be better as an additive to improve a pool of diesel, because the octane or cetane number is very high. So by itself, it will be a waste to use that beautiful diesel for burning itself, but we can use it to mix it with a lower quality diesel from conventional refinery and improve that and give value, real value to those oil. Also, many of the products, depending on the feedstock, because they are so different between them, that you can have something that can be converted into synthetic oil, similar to uh, fossil fuel, and then actually be mixed and co-processed, not in 1 to 5%, 100%. If the amount of that oil is enough, you can process that oil as 100% as a conventional oil, or you can mix it to gain some political advantage because you are using, let's say, 50% of green oil in 50% of a fossil fuel, so you get some revenue for that, government revenues for that, incentive. So we are a really good bridge to them.